Tonight we begin near the end of a very long journey. For generations, Alpha Centauri would have been only a destination on charts and instrument displays, a small point of light more than 4 light years from Earth. Then, as the ship drew closer, that point would begin to separate into a real stellar neighborhood. Positions would shift, brightness would change. What had once been a name inherited from distant ancestors would finally become a place outside the windows. But crossing the distance would not mean the journey was finished. Before anyone could think seriously about a new home, the ship would have to solve one quieter problem first. It would have to stay. The ship might already be inside the Alpha Centauri system and still be moving far too quickly to remain there. That distinction matters because interstellar travel has two very different problems. The first is gaining enough speed to cross the distance between stars. The second is giving that speed back. A spacecraft in deep space does not slow down simply because its destination has appeared ahead. Motion has to be changed deliberately. Engines can throw mass forward. A sail may interact with light or charged particles. Other methods have been proposed, but every design faces the same underlying requirement. To stay, the vehicle must lose enough velocity for its path to become controlled. Without that, an arrival becomes a flyby. A fast probe can still do useful science during a flyby. It can take images, sample radiation, and measure magnetic fields while passing through. But it may have only hours or days near the places it crossed years of empty space to reach. Then the target falls behind, and the probe continues outward. For a settlement ship, that would not be enough. Its passengers would need time measured not in hours, but in years. They would need to compare worlds, watch weather systems, map radiation, study possible resources, and change their plans when the first interpretation proved incomplete. All of that begins only after speed has become something they can control. This is why the most impressive cruise speed is not automatically the most useful one. A faster crossing shortens the voyage. That can reduce the time people and machines spend exposed to the slow damage of long travel. It can reduce the number of generations born between departure and arrival, but it also means the ship carries more kinetic energy into the destination system. That energy cannot simply disappear. The faster the craft is moving, the more demanding the braking problem becomes. Propellant may have to be carried across interstellar space only to be used at the end. A braking system adds mass, and that mass had to be accelerated at the beginning. Protective shielding adds more mass. Even small particles become more serious hazards as relative speed rises. Probe studies make this trade-off especially clear. Some light sail concepts have examined journeys at a few percent of the speed of light. At those speeds, crossing the distance to Alpha Centauri can fit within roughly a century. But when the design includes controlled deceleration rather than a simple flyby, the total mission can become much longer. In one study of an extremely small probe, the braking phase alone added decades. That example does not tell us how a generation ship would be built. The scale is entirely different. What it does show is something more basic. The journey does not end when the star is reached. The mission changes character when motion becomes control. A cautious ship might begin slowing long before the target stars dominate the view. Its instruments would keep watching while the braking system worked. Navigation would become more precise. The crew would learn that the final years of the voyage were not a dramatic plunge toward a new world, but a gradual exchange of speed for options. And once the ship finally had those options, another question would become possible. Not simply, where is Alpha Centauri? But where, inside this entire system, should the settlers go first? Once the ship could remain near Alpha Centauri, the destination would stop looking like a single point. It would become a system. Alpha Centauri A and Alpha Centauri B orbit one another as a close stellar pair. Both are broadly similar to the Sun, though not identical to it. Farther away is Proxima Centauri, a small red dwarf that belongs to the same wider system and carries confirmed planets of its own. That arrangement changes the meaning of arrival. A settlement mission would not need one perfect world. It would need a useful map. One location might offer a promising surface. Another might provide a safer orbit. A small body could contain useful material. An empty region of space might be valuable simply because it gives the ship time to observe everything else without committing too early. From Earth, it is tempting to imagine one destination in advance. Proxima b naturally attracts that attention. It is a confirmed planet with a mass close to Earth's. Its orbit is very tight, lasting only a little more than 11 Earth days. Yet because Proxima Centauri is faint compared with the Sun, the planet receives an amount of stellar energy that places it within the star's conventional habitable zone. Those measurements make Proxima b important. They do not make it a home. The distinction is easy to lose because a planet name feels complete. Once an object has a mass, an orbit, and a place on a chart, the empty spaces around those numbers can become almost invisible. But for the people aboard the ship, the empty spaces would matter most. They would want to know whether the planet has an atmosphere, and if so, what that atmosphere contains. They would need to understand surface pressure, radiation exposure, temperature patterns, available water, and the chemistry of the ground. They would need to know whether useful materials could be reached without placing equipment in dangerous terrain. Current measurements do not answer all of those questions. That is not a failure of astronomy. It is simply the boundary between detecting a world and knowing what it is like to live near one. The same logic would apply across the rest of the system. Alpha Centauri A and B may host additional worlds that remain difficult to detect. In 2025, observations with the James Webb Space Telescope produced strong evidence for a candidate giant planet around Alpha Centauri A, but it remains unconfirmed. By the time a settlement ship arrived, the system could turn out to be more complicated than its ancestors expected. That possibility would make flexibility more valuable than certainty. Instead of carrying a single landing plan, the ship would need branches. If Proxima b proved suitable for close study but poor for immediate settlement, the crew could remain in orbit. If another world offered better resources, machines could be sent there first. If no planet was ready for people, asteroids, moons, or constructed habitats might still provide material, shelter, or staging points. The ship would not need every location to be comfortable. It would need several locations to be useful. That is a quieter way to think about interstellar settlement. The first map would not be a picture of a chosen home. It would be a map of options. Each confirmed object would add one possibility. Each uncertain measurement would keep another path open. A safe orbit might matter as much as a promising surface. A small rock with accessible material might become more important than a beautiful planet with too many unknowns. By then, the settlers would already have learned one lesson from the voyage itself. A destination is not valuable because it looks final. It is valuable because it gives you room to choose what comes next. And among all those choices, Proxima b would still stand out. Not because it had already proved itself habitable, but because it was the nearby world with enough measured promise to deserve the closest look. The next question would be more demanding. What exactly would the ship be looking for? Proxima b would deserve careful attention because it sits in an unusually interesting position. It is close to Earth in mass, and it receives enough energy from its star that liquid water could be possible under the right conditions. Those two facts are enough to justify curiosity. They are not enough to describe a place. The phrase habitable zone can sound more complete than it really is. It refers mainly to the amount of energy a planet receives from its star. Under suitable atmospheric conditions, that energy could allow liquid water to exist on the surface. But the definition does not tell us whether the atmosphere is suitable. It does not tell us whether water is actually present, and it does not tell us whether the surface would be safe for people. For the settlers, those missing details would be the real beginning of the investigation. Proxima Centauri is much smaller and dimmer than the Sun. To receive enough warmth, Proxima b orbits very close to it. 1 year on the planet lasts only a little more than 11 Earth days. That tight orbit creates both opportunity and difficulty. The planet receives useful warmth from a faint star, but it also lives close to a star known for strong magnetic activity and powerful flares. High-energy radiation matters because it does more than warm a surface. Extreme ultraviolet light and X-rays can heat the upper layers of an atmosphere. Over very long periods, that heating can help gas escape into space, especially if other protective conditions are weak. A 2016 estimate suggested that Proxima b may receive roughly 30 times the extreme ultraviolet exposure Earth receives from the Sun, and around 250 times the X-ray exposure. Those numbers sound severe, but they do not give us the final condition of the planet. Atmospheric survival depends on several things we do not yet know. How much atmosphere did the planet begin with? What gases are present? Can geological activity replace some material that escapes? Does the planet have a magnetic field? And if it does, how effective is it? A thick atmosphere might have endured despite strong stellar activity. A thinner one might have been reduced substantially. Both remain possible. The same uncertainty appears when we think about the planet's rotation. Because Proxima b travels so close to its star, tidal forces may have slowed its spin. It could be rotating synchronously, with the same hemisphere generally facing the star. Other rotational states, including a 3-to-2 resonance, are also possible. That distinction would matter greatly for climate. If one side received much more continuous starlight than the other, the surface might divide into very different thermal regions. But even then, the result would depend on the atmosphere. A dense atmosphere can move heat. So can an ocean. Winds and circulating water can carry energy away from the bright side and toward colder regions. With enough redistribution, the contrast between hemispheres might be less extreme than a simple picture of permanent day and permanent night suggests. With very little atmosphere, the contrast could become much stronger. This is why the ship would not arrive looking for one number called habitability. It would be looking for a pattern. Orbital instruments could study the atmosphere if one were present strongly enough to be measured. They could watch how the planet responds to stellar flares. They could map temperature differences, search for signs of clouds, and measure how radiation changes around the world. Robotic probes could go closer. They could test the ground, search for accessible water or ice, measure radiation at different locations, and compare regions that receive very different amounts of starlight. A sheltered basin might be more useful than an open plain. A region with ice might be valuable even if it was not comfortable. A place with moderate temperatures might still be poor for settlement if radiation remained too high. Every attractive feature would have to be considered beside its cost. That is one reason a planet can look promising from many light years away and still resist a simple label after arrival. The measurements from Earth would have done their job. They would have identified Proxima b as a real world worth investigating. But they would not have chosen a home for anyone. By the time the settlers reached this stage, the central question would already be changing. At first, they might have asked which planet in Alpha Centauri was best. Now the more useful question would be different. How much could they safely commit before the system had earned their trust? And if the surface was still uncertain, the safest first home might not be on a planet at all. If the surface was still uncertain, the most valuable place in the system might be the one the settlers already trusted, the ship itself. After generations in transit, it would be easy to think of the vessel as something that had finished its purpose. It had carried people across interstellar space. The stars ahead were finally real. A planet waited below, but the ship would also be the only habitat in the system with a long history of keeping those people alive. Its air systems were known. Its water loops had been repaired before. Its medical spaces, workshops, farms, storage rooms, alarms, and emergency procedures had all survived real failures. That record would matter more than appearances. A new world could look calm from orbit and still contain problems that took months to reveal. Dust might damage seals. Soil chemistry might interfere with crops. Radiation could vary across the surface. Weather patterns observed during one season might change sharply in another. None of those problems would automatically make settlement impossible. They would make commitment expensive. So the first home near Proxima b If the planet remained the leading candidate, might stay above it. From orbit, the settlers could watch without placing the entire community inside an environment they still understood poorly. They could map radiation over time. They could follow weather patterns. They could compare possible landing sites through more than one season. They could send instruments into places that looked promising and withdraw from places that did not. Most importantly, they could change their minds. That may be the first real principle of settlement. Early decisions should be reversible. A small surface outpost can be abandoned. A robotic survey can be redirected. An orbital station can move. A civilization that sends nearly everyone to one untested site has much less room to learn from mistakes. This does not mean remaining in orbit forever. It means allowing evidence to decide the order of commitment. The safest first site might not be the most beautiful one. It might not even be on Proxima b. The settlement could begin as a network, the old ship holding most of the population, smaller stations and probes extending outward, and short surface visits testing equipment before longer stays. Nothing in that arrangement would look like the traditional image of founding a new world. There might be no first morning when everyone stepped outside together. Instead, arrival would spread across years. One instrument would survive a season. One shelter would remain sealed. One sewer system would continue through a period of poor conditions. One crew would spend a few weeks below and return safely. Each success would justify a slightly larger commitment, and each failure would remain limited enough to teach something without ending the larger mission. This is also where robots would become especially valuable. Machines can accept risks that people should not have to accept first. Robotic reconnaissance would also turn vague questions into practical ones. Can local material be moved? Can water be extracted? Can power systems stay clear of dust or ice? Can equipment survive the temperature range? Can a damaged vehicle return to orbit? Those answers would shape settlement more directly than any distant image of a promising planet. By this point, the voyage would have changed again. The settlers would no longer be asking for the best world in the system. They would be asking which dependence they could safely remove next. First, they had depended on speed, then on the ship. Soon, they would depend on machines working beyond the hull. And that would introduce another problem. A robot can prepare a place for people, but only if something can keep the robot working. A robot can prepare a place for people only while the systems behind that robot continue to function. At first, that sounds like a small qualification. A machine needs power, it needs software, it needs replacement parts. If something breaks, another machine can repair it. But each of those answers opens another dependency. The power system needs maintenance. Maintenance needs tools. Tools need materials. Materials have to be found, processed, shaped, and checked. And eventually, somewhere in that chain, there may be one component that nobody in Alpha Centauri can yet make. That is the difference between using robots and becoming independent through robots. A settlement could think of this problem as a ladder. The lowest rung is energy. Can local systems produce enough power to keep essential equipment running through ordinary changes in weather, dust, darkness, or equipment failure? Above that comes material. Can machines obtain water, metals, carbon-bearing compounds, or useful rock from somewhere in the system? Then comes processing. Raw material is rarely useful in the form in which it is found. Ice has to be extracted and purified. Metal-bearing rock has to be separated and refined. Structural material has to be made with predictable properties. Above processing comes fabrication. Can the settlement turn those materials into pipes, brackets, pressure vessels, cables, seals, and machine parts? Then comes repair. Can one machine diagnose another, remove the damaged component, produce or retrieve a replacement, install it, and confirm that the repaired system is safe to use? Each rung makes the settlement more capable, but climbing one rung does not automatically close the ones above it. A robotic workshop might be able to make a strong steel bracket while remaining completely unable to manufacture the sensor that tells a pump when to stop. It might rebuild a simple motor but not the electronics controlling it. It might produce kilometers of cable while depending on imported connectors, insulation, bearings, lubricants, or computer chips. That unevenness would probably define the early decades of local industry. The easiest loops would close first. Water is an obvious example. If accessible reserves exist, local water could support drinking supplies, agriculture, chemical processing, shielding, and perhaps propellant production, depending on the technologies being used. But complexity rises quickly, so independence would not be measured by how much material came from Alpha Centauri. It would be measured by how many important failure chains could be completed there. Imagine a water pump stops. A shallow repair system can identify the failed module and replace it with a spare brought from Earth. A deeper system can open the module and replace the worn bearing. Deeper still, it can manufacture that bearing locally. But even then, the machine that manufactures the bearing needs cutting tools, sensors, power electronics, control software, and its own supply of replacement parts. The ladder continues. This is why a settlement would not become autonomous through one remarkable factory. It would need overlapping capabilities, several power sources, more than one workshop, different ways to move material, machines able to repair common failures in other machines, inventories designed around the parts most difficult to reproduce, and enough diagnostic knowledge to recognize when an apparently minor problem is beginning to spread through several systems at once. This would make progress look slower than a dramatic image of automated cities rising before the settlers arrived. But it would make each step more useful. The useful question is not whether the robots are advanced. It is how far a failure can travel before the settlement reaches something it cannot replace. Early on, that boundary might be very close. A damaged computer, a failed medical instrument, a specialized valve, a chemical catalyst, a precision component stored in a sealed container because nobody yet knows how to manufacture another one. Those objects would connect the new settlement to the civilization that built the ship. Over time, some of those connections could disappear. A replacement part once taken from storage might later be produced in a workshop. A material once rationed carefully might be refined locally. A repair once handled by one specialist might become routine work understood by several people and several machines. The settlement would be climbing the ladder one dependency at a time, and this would change the role of the ship again. At first, the ship would contain almost every difficult answer. Its stores would hold the rare parts. Its workshops would contain the best tools. Its archives would contain procedures for systems nobody in the new settlement had yet rebuilt from first principles. Its power and life support machinery would remain the safest fallback. As local capability expanded, fewer failures would need to return there. The ship would still matter, but its importance would begin to change from immediate survival toward reserve. That shift would be subtle. There might be no ceremony for the first locally manufactured component that replaced the last imported spare of its type. No one might notice the particular week when a workshop stopped asking the ship for routine parts. But those quiet changes would matter more than a flag or a footprint, because machines alone would never complete the settlement. Someone would still need to understand them. Someone would need to notice when a repair was unusual. Someone would need to teach the next person why a system had been designed a certain way, and what to do when the usual answer failed. The closure ladder would therefore extend beyond material and machinery. Eventually, it would reach people. And the next test would be whether the settlement could preserve not only the systems that kept everyone alive, but the knowledge required to rebuild them. The settlement would become more secure each time an essential ability stopped, belonging to only one machine, one room, or one person. That is where resilience would begin to look less like engineering and more like ordinary life. Redundancy would not make the settlement fully independent. It would make failure smaller. That matters because a community can survive many serious problems if those problems remain local. A damaged habitat is dangerous. It is far more dangerous if every person lives inside it. A failed power system is serious. It is worse if there is no second system able to take over. A crop disease may destroy one growing area. It becomes a civilizational threat only if every harvest depends on the same plants, the same environment, and the same assumptions. So the early settlement might deliberately avoid becoming one large city too quickly. Instead, it could grow as several connected places. One habitat might remain close to the original ship. Another could support surface work. A smaller outpost might sit near a useful resource. Workshops could be duplicated gradually. Food stores could be distributed. Emergency shelters could remain stocked even when they were rarely used. The result might look inefficient. There would be spare equipment sitting idle. Some rooms would remain empty. Several people might be trained for jobs that usually required only one. But unused capacity is not always waste. Sometimes it is what turns an accident into an inconvenience rather than a crisis. The same principle applies to knowledge. During the voyage, some systems might have been maintained by specialists whose expertise came from long practice. They would know which alarm could wait, which vibration meant trouble, and which repair procedure looked simple on paper, but almost never was. That kind of knowledge is difficult to store completely in an archive. Instructions can preserve steps. They cannot preserve every judgment. A settlement that depended on one experienced engineer would therefore contain a hidden single point of failure, even if the machines themselves had backups. The solution would be teaching. Not teaching as a secondary cultural activity, but as part of infrastructure. Every important skill would need more than one living path into the future. A technician would train someone else before retirement. Medical knowledge would be shared across teams. Children would learn not only how the settlement worked, but why certain systems had backups, why some doors remained sealed, and why an apparently unnecessary reserve of parts was never casually consumed. Over time, the local community would begin producing something the original ship could not simply unload from storage. Experience. The first generation might understand Proxima B through models prepared before arrival. The next would understand it through years of weather records. Later generations might know which surface routes remained passable, which materials caused trouble in machinery, which crops adapted best to local conditions, and which pieces of equipment lasted longer than their designers expected. That knowledge would belong to the new system rather than the old one. And as local knowledge grew, the relationship with Earth would change too. Messages could still travel between the stars. Advice could still arrive. Designs, scientific results, art, and history could still be exchanged. But no message could serve as an emergency repair team. Even at light speed, communication across more than 4 light years would take years in each direction. By the time a question reached Earth and an answer returned, a practical problem might already have required a local decision. So the settlement would have to become intellectually self-reliant long before it became completely industrially self-reliant. People would need the authority and the confidence to adapt inherited designs. They would need to test new solutions, would need to know when an old procedure no longer matched a new environment. That is another kind of closure. Not the ability to reproduce every machine, but the ability to continue making good decisions when the original designers are no longer available. Eventually, the community might notice that several old dependencies had faded. A failed pump could be rebuilt locally. A crop problem could be handled without emergency reserves from the ship. A damaged habitat could be evacuated into another. A specialist could die or retire without taking an entire field of knowledge with them. A generation could grow up that had never seen Earth except in recorded images and still understand how to maintain the systems around them. At that point, the settlement would no longer be just a collection of equipment carried from one star to another. It would be becoming a society. Yet even then, one tempting question would remain. How many people would be enough? It sounds as though independence should have a number. A population large enough to preserve skills, large enough to maintain genetic diversity, large enough to survive accidents and continue across generations. Researchers have explored versions of that problem with computer models, but the answers depend heavily on the assumptions placed inside them. So the final test cannot be reduced to a single head count. The more useful question is harder and quieter. What could this settlement lose tomorrow and still continue? That may be a more useful measure of independence than population alone. There have been attempts to estimate how many people a multi-generational interstellar population might need. One 2018 simulation found that, under its specific assumptions about reproduction, mortality, pairing, and a 300-year voyage, an initial crew of 98 people could maintain a genetically healthy population. But that result is not a universal minimum. Change the assumptions, and the answer changes with them. A settlement at Alpha Centauri would face another problem as well. Genetic continuity is only one part of survival. A community might contain thousands of people and still depend on one irreplaceable factory. It might have a large population but only one hospital capable of complex treatment. It might grow enough food in an average year while having no backup if one agricultural system failed. Numbers alone would not reveal those weaknesses. So the settlers would need another test. Could they lose one habitat and keep living? Could one power system fail without shutting down the others? Could a workshop burn, flood, or depressurize without taking the settlement's repair capacity with it? Could several experienced specialists disappear from the workforce and leave enough knowledge behind for other people to continue? And eventually, the largest question of all, could they lose the original ship? Not because anyone would want to destroy it. The ship might remain valuable for centuries. Its archives, old machinery, storage spaces, and history could continue serving the community long after arrival. But value and necessity are different things. At first, losing the ship might mean losing the safest habitat, the best tools, the largest reserve of spare parts, and perhaps the only reliable path back from a failed surface settlement. Later, some of those functions might exist elsewhere. A second habitat could shelter the population. Local workshops could reproduce common components. Food could come from several independent systems. Medical care could continue in more than one location. Knowledge could exist in people, institutions, and archives distributed across the settlement. Then one day, perhaps without ceremony, the old ship would cross an invisible threshold. Its loss would still be painful. It would no longer be fatal. For this story, that is the most useful definition of practical independence. Not a flag. Not a particular number of people. Not the first child born beneath another sun. Independence begins when no single inherited system can decide whether the community has a future. By then, Alpha Centauri would no longer be only the place the settlers had reached. It would be the place from which they could continue. Years after arrival, the old ship might still be visible from the settlement. Perhaps it would cross the evening sky as a small moving point, bright for a few minutes in the light of another sun. The people below would know what it had once meant. For their grandparents or their grandparents' grandparents, that vessel had been almost everything at once. Home, workshop, archive, hospital, shelter, and the only reliable place to return when something went wrong. Now its meaning would be different. A pump might fail in one habitat, and another would keep working. A damaged part could be made nearby. Food would grow in more than one place. A young technician might repair a system using knowledge learned from someone who had never seen Earth except in old recordings. Nothing about that life would feel complete or permanent. There would still be difficult seasons, failed equipment, disagreements, and questions no one could answer yet. But the community would no longer be balanced on a single inherited machine. That change might be easy to miss. There may be no ceremony for it. No exact morning when someone announces that the settlement has become independent. Instead, the threshold would appear in ordinary moments. A repair completed without opening the ship's reserves. A harvest recovered after one growing room failed. A medical problem handled locally. A new generation learning not only how to preserve the old systems, but how to change them when the new world demanded something different. Long ago, Alpha Centauri had been a point of light. Then it became a destination, then a system to be measured, then a place where every decision had to remain reversible. And eventually, almost without noticing, it could become something simpler. Home. Above it, the ship would still pass through the dark, still useful, still remembered, but no longer carrying the future by itself.